All right, everybody, welcome back. Ready for another deep dive.
Let's do it.
Today we are talking about acoustic levitation.
Ooh, that sounds cool.
Yeah, using sound waves to make things float. How cool is that?
That's pretty wild. I've seen some videos of it, but I don't really understand how it works.
Yeah, it's one of those things that just seems impossible.
Right.
Like, how can sound be strong enough to overcome gravity?
Well, that's exactly what we are going to get into today.
Perfect.
We're going to break it all down, step by step, and by the end of this deep dive, you'll be able to impress all your friends with your knowledge of acoustic levitation.
Our main source today is this fascinating student project report on the topic. I'll admit, when I first saw the title, I thought, okay, another science fair project. But let me tell you, this report dives deep. It's like way more detailed and intricate than I ever expected.
I'm intrigued.
So, to set the scene, imagine you're at a science fair, right? And you see this little styrofoam ball just kind of hanging there in midair.
Okay, I can picture that.
Yeah.
Been there, done that.
Exactly. But there are no strings, no magnets, no tricks. It's just flowing there, seemingly defying gravity. And the secret, sound waves.
That's acoustic levitation in action, right?
Right. Now, this isn't some brand new discovery. You ready for this?
Hit me.
Acoustic levitation was first achieved all the way back in 1933.
Whoa, 1933. That's almost a century ago. What was the setup like back then? I mean, technology wasn't exactly what it is today.
Well, think old school. Scientists used quartz crystals, vibrated at high frequencies to create the sound waves.
Ah, so that's where the sound came from. But how do they actually lift something with it?
Okay, so here's the key. They position a reflector just right to create what's called a standing wave. And that, my friend, is the magic behind acoustic levitation.
A standing wave. Okay, I'm not quite picturing that yet. It sounds like a wave that just kind of stands still.
You're actually not far off. Think of it like this. You've got these sound waves, right, traveling between a speaker and a reflector, kind of bouncing back and forth.
Okay, makes sense so far.
Now, as these waves travel, they interfere with each other.
Like, they crash into each other.
Sort of. At some points, the waves reinforce each other, creating these zones of maximum pressure. These are called antinodes.
Antinodes, got it.
And then at other points, the waves cancel each other out, creating these zones of minimum pressure. And guess what these are called? Nodes. You got it. And the cool thing is, these nodes and antinodes, they stay put. They don't move along with the waves, hence the name standing wave.
So it's kind of like a tug of war between the sound waves, and those nodes and antinodes are the spots where the rope stays still.
Exactly. Brilliant analogy. And it's those nodes and antinodes with their different pressure levels that create the force needed to lift things.
Hold on a sec. So you're saying that these teeny tiny pressure differences within the standing wave can actually be strong enough to counteract, like, gravity. My brain's having a hard time wrapping itself around that.
I know, right? It's mind-boggling. But think of it like this. Maybe this will help. Imagine you're holding a ping pong ball, and you blow a jet of air straight up at it.
Okay, the ball floats in the air. Classic demonstration.
Right. So, in acoustic levitation, those pressure variations within the standing wave, they act kind of like that jet of air, pushing against the object and saying, nope, to gravity.
Huh. Okay, I think I'm starting to get it. The pressure differences create a sort of invisible hand that keeps the object suspended.
Exactly. Now, our Student Friends report, it lays out 3 key conditions that need to be just right for acoustic levitation to actually work. Kind of like the recipe for this sound magic, you know?
Ooh, a recipe for levitation. Let's hear it.
Condition number 1, and this one's pretty crucial, particle size matters.
Particle size. You mean the size of the thing you're trying to levitate?
Precisely. The object has got to be smaller than the speaker itself. If it's bigger, well, things get messy. The sound waves start reflecting off the object's surface, messing up the standing wave.
So it's like, if the object's too big, it becomes its own reflector, and the whole carefully crafted wave pattern gets messed up.
You nailed it. It's like trying to balance a house of cards on a wobbly table. Not going to end well.
Makes sense. But wait, what about those cool videos you see online where they're levitating like water droplets or even little insects? Those aren't exactly tiny.
Ah, you got me there. But for those larger objects, scientists, they've got a trick up their sleeve.
Ooh, lay it on me. What's the trick?
Multiple speakers. They arrange them in specific patterns, often in a bowl shape, to create this, like, super-powered sound field.
Clever. So more speakers, more power, bigger levitation.
Not just more power, but control. By tweaking the phase and amplitude of the sound waves from each speaker, they can pinpoint the exact spot where the pressure's just right to lift heavier things.
Whoa, that's some next-level sound engineering right there. Okay, on to condition number 2. What's this one about?
This one's all about location, 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 where those particles like to hang out within the standing wave.
Wait a minute. Location. But if there's this constant push and pull from the changing pressures in the wave, wouldn't the object just be, like, vibrating wildly rather than actually floating?
That is a great question, and you are totally right. It's all about the pressure. But here's the thing. To make this work, you got to match the frequency of the sound waves to the object's natural resonant frequency.
Resonant frequency. Now, that rings a bell from, like, high school physics.
Yeah.
Something about how objects vibrate at specific frequencies.
Exactly. It's like finding the object's sweet spot on the sound waves, where it can ride the pressure changes smoothly without getting tossed around like a salad.
Ooh, so it's like syncing up the sound waves and the object's vibrations so they work in harmony.
Precisely. Our students report, you give this super helpful example with a 2mm styrofoam ball.
Huh.
Picture this, right? The ball's in a node, the zone of minimum pressure.
Okay, got the ball, got the node.
Now, the pressure from the surrounding antinodes, the high-pressure zones, pushes the ball towards the center of the antinode.
So far, so good.
But then, bam, the pressure flips. The node becomes the high-pressure zone, and the antinode becomes a low-pressure zone. So guess what happens to our little styrofoam buddy?
It gets pushed back towards the node. It's like a cosmic ping pong game.
You're catching on quick, and this back and forth, it's happening crazy fast, thousands of times every second.
Oh, wait, thousands? Like, how many thousands are we talking here?
Try up to 40,000 times per second.
40,000? That's insane. So the ball is basically getting bombarded by these pressure changes, but it's happening so rapidly that it looks like it's just calmly floating.
Spot on. Kind of like a hummingbird's wings, you know? They're flapping so fast they just blur together, and it looks like the bird's effortlessly hovering.
Wow, that's an awesome analogy. Okay, I'm ready for condition number 3. Tiny particles. Different rules. What's the scoop on this one?
All right, so buckle up because things are about to get weird. When we're talking about particles that are super small, like nanoscale small, things change.
Weird in what way? Do they levitate upside down or something?
Not quite upside down, but close. These tiny particles, they actually prefer to levitate in the antinodes, the high-pressure zones.
Wait, seriously, that's the opposite of what we've been talking about. Why would they do that?
It's all about that size and wavelength connection again. If a particle is way smaller than the wavelength of the sound, it gets pushed around by the pressure gradients in the way that ends up trapping it in those high-pressure antinodes.
So it's like they're surfing those high-pressure waves,
Right.
riding the sonic crest.
Exactly. And for this to work, the particle's diameter, it's got to be less than 10% of the sound wave's wavelength.
So size really does matter in the world of acoustic levitation. Big particles in the nodes, tiny particles in the antinodes. It's like a cosmic dance floor, with everyone finding their groove.
You got it. And it's amazing, right? Something as everyday as sound, it can create these crazy, complex, super fascinating phenomena.
It really is, and honestly, I bet this is just scratching the surface. With scientists pushing the boundaries of what's possible with sound, who knows what kind of amazing applications are waiting to be discovered.
Right. And thinking about all this levitation talk, I can't help but wonder, if we can levitate a styrofoam ball, a water droplet, even a little insect, could we, like, one day levitate bigger things?
Bigger things. How big are we talking?
Well, maybe even a person. Yeah. I know it sounds crazy, like something straight out of a sci-fi movie, but hey, if sound waves can defy gravity on a small scale, who's to say what the future holds?
That's a pretty wild thought. Personal levitation devices powered by sound. Sign me up for that.
Right. Imagine, like, sound-powered hoverboards zipping around. Okay, maybe I'm getting ahead of myself.
Hey, a little futuristic dreaming never hurt anyone.
Exactly. But anyway, thanks for joining us on this deep dive into the world of acoustic levitation. It's been a wild ride.
It really has. Definitely learned a lot more than I expected. Now, excuse me, I've got to go find some styrofoam balls and speakers.